In part D, we're going to go ahead and finish up with physical and chemical properties of alkanes and cycloalkanes. So starting off in slide 40, most of this you should already know. Alkanes and cycloalkanes are insoluble in water, having learned in 101 that they are nonpolar and water is polar, hence they do not mix. And let's move on. Alkanes and cycloalkanes have densities lower than water, so they have a density of less than 1. Boiling points of alkanes and cycloalkanes increase as chain length, ring size increases. So the bigger the alkane, then the higher the boiling point. So as we start getting into, as we start to go from, for example, butane to hexane, the boiling point increases, and you'll find that the structure of the substance goes from a gas to a liquid. And when you get up to 10, 11, 12 hydrocarbon atoms long, then it'll turn into a solid, such as a wax. So make sure you know those general properties. This last one's a little bit more difficult, so let's go ahead and go to ISIS so we can understand this a little bit more clearly. Boiling points of alkane and cycloalkane isomers decrease as branching increases. So going over to ISIS. Here we have two examples. The first one I'm going to lasso. This is 4,4-diisopropyl heptane. There are those special alkyl branch names you have to memorize. So we see those also in action here. Compare this one to this 13-carbon chain called a tridecane. So they have the same molecular formulas. They are different structural isomers, but notice how the example on the left is more branched. It has more branches than the one on the right. The one on the right is spread out. So here's the rule. The more branched it is, the lower the boiling point. We really explain why this occurs in the chapter 3-4 slides, but for right now this is a property you're going to have to memorize. So let's go ahead and move on to chemical properties. Here are examples of chemical properties. When we use the term chemical properties, we're referring to any type of known chemical reaction that can occur. So let's go ahead and open up this example right here on ISIS. On the top one, we have a combustion reaction. Here I have ethane, for example. It's any alkane or cycloalkane. And we combine it with oxygen, and really we should put in here, it does require, it requires a catalyst such as heat, go figure. And it produces water and carbon dioxide. Now here is another type of chemical reaction you have to know. This is called halogenation, also known as free radical halogenation reactions. In this case, it's any alkane or cycloalkane, and you add in a halogen such as chlorine gas, fluorine, or bromine, or iodine. And basically what happens is one of the hydrogens is swapped out with another one of the chlorines, and they come together forming a brand new, as I highlighted here, hydrogen chloride, and a brand new 1-chloroethane. So in Chemistry 101, this was an example of a double replacement reaction. We'll investigate future types of chemical reactions where the derivative atom is already there. So let's go back to the slides. So in the following examples, we're going to start off with a hydrocarbon derivative, and that's where the chemical reactions like to occur. It also has a huge factor on the physical properties of the overall alkane. So we define functional groups as a set of atoms, and they're essentially derivative atoms, anything other than carbon and hydrogen, that give them unique physical and chemical properties. The only exception is alkenes and aromatics, where technically there are missing hydrogens forming pi bonds, and it's the pi bonds that are considered the functional group. But for the most part, look for the derivative atoms, and that is where the functional group is present. Here are examples of hydrocarbons with functional groups. With the derivative atom chlorine attached, this is the halides. With OH attached, with oxygen attached, forming a OH group, we call these alcohols. And here is a third functional group. We call these ethers when they're between two carbons. We'll get into more in recognizing them in future chapters, but for right now, chemists love functional groups because that's where the chemical reactions occur. Here is alcohol. So for example, when it enters the body and the body neutralizes alcohol, the first place it reacts with is the alcohol group, forming what's called a aldehyde. But bottom line is that's where the chemical reactions occur. So we can dictate what type of chemical reactions occur depending on what type of functional group has been added. And you can think of most of organic chemistry as being the addition or manipulation of these various functional groups. Here are the various categorical names, along with their formulas and examples. And as the weeks go along, we're going to investigate each class of functional group and their various naming schemes, physical properties. And finally, we'll investigate various chemical properties of each of these functional groups, along with some of the more popular chemical reactions found in industry. And finally, we'll investigate various chemical properties of each of these functional groups, along with some of the more popular chemical reactions found in industry.